mainly focusing on the differences between forwarding and routing. So I'm going to make sense, why do we have routing within the network layer, not with the actual data link? What are the differences between routing and forwarding? Are they not the same? I'm going to describe one of the routing algorithms called the star algorithm. It's a link state, depends on the shortest path. How do you send information? This is a practical part where I need you to get involved. I'm going to give you an example, and I'll ask you to do the other half, and I'm going to do it again. I'm trying to make this lecture short because I want to focus mainly next lecture on addressing, i.e. subnetting. How do you do subnetting? I might give an introduction with subnetting, but the practical part of ARP and class interdomain part of addressing will be the third lecture. So it might be 2 lectures, might be 3 lectures on network layer. We'll see how things will work on. I think the register is not working for the electronic one, so I've already circulated your manual one. If you just type your name there, and we'll check it in the end. Okay, so let's start. What's the main duty of network layers? Remind me. The main duties of the network layer. So the switch mainly was forwarding the packets from coming in, the incoming link to the outgoing link. What about the routers? What do they do?
They're passing the packet.
Again, passing the packets from the incoming to the outgoing, and there's an extra responsibility, is routing the full direction towards the destination. So we are not dealing with one router. We might be dealing by multiple routers to reach a destination. So if I'm sending information through 3 different routers, the forwarding term mainly means just passing on one router. Meanwhile, routing means describing the full direction of that packet. So I'll explain the full details in a moment. But let's go, what are we going to describe today? Understanding some of the principles behind network layer and services, routing, i.e. path selection. That will be the part where I show you the algorithm, some of the routing algorithms available. I'm going to focus this year on just link state. Sometimes we focus on different ones like vector one and open short path selection. This year I'm focusing on link state, the star algorithm. Addressing, we're going to describe subnetting and how subnetting are being allocated to different users. How each user will have its own IP address. Who decides that? Is it the router? Is it the user? Is it the admin? The internet service provider? That will be the differences. Some of the network layer services models, as I said, there are models available with each service in addition to passing on the datagrams. Going to that in details. Forwarding versus routing, that will be part of the lecture today. How router works, I'm going to look at the fabric of the router. How is it different from the switch? So what do you have inside the router compared to the switch? How do they actually pass information on? And finally, we'll have ARP, Address Resolution Protocol, part of this notes, where I'm going to associate between your IP addresses and your MAC addresses. Because why would I need one of them or need both of them to deliver to the right destination? I'm going to describe exactly why both of them are important at the moment. Your MAC addresses and your IP addresses. So let's start, first of all, with the network layer. How does it look like? Where exactly are we working on? How the router will look like? What are the architecture of each one of those nodes and the router itself? So I think by now you remember the encapsulation process and how can a datagram be passed on from a source to as a destination. Mainly is the transport segment, coming for your 4th layer, will be passed on from the transport layer towards your network layer, i.e. passing on the actual segment. And therefore, on the sending side, it encapsulates. The sending side try to encapsulate that segment by adding a header file of the datagram, creating what we call a datagram. Therefore, we forward it towards your lower layers. On the receiver side, though, the delivery will be a segment towards the right transport layer. So in a matter of fact, it's another way around. As we saw in the encapsulation process, message passed on from the higher layers towards the lower layers. Meanwhile, on the receiver side, goes down from the lower layers towards the higher layers. So now the network layer in the center side is encapsulating the message, passing on to the lower side. Meanwhile, on the other side, i.e. the receiver, passing on to the transport layer. This will go through a different set of routers. So again, routers architecture mainly are 3 layers. You have your physical layer, your data link, and now you need the router. You need your network layer. In the switches, if you make a comparison, we have just only two layers. Mainly your physical and your data link. Because your network layer are not needed. I'm not dealing with IP addresses. I mainly was dealing with MAC addresses only. So therefore, we didn't need the actual third layer. Meanwhile, with the IP addressing, it's mainly to have your network layer to deal and try to process your IP addresses. Just a short reminder of how does IP addresses look like. It's not a reminder to be fair, but most of you know how an IP address looks like. What is an IP address? Can anyone remind me? Does he know what an IP address? What does it consist of? Numbers. How many numbers? How many parts? So we have two types of IP addressing. I'm going to explain them in details. Well, we have an IP version 4 and we have an IP version 6. The old one, version 4, which is still used by the moment, is mainly 4 octets, i.e. 4 bytes. There are 4 parts. Consist of a decimal number, starts from 0 up to 225. So usually an IP address will look like, I think most of you is, for those who are interested in how to set up your own router or however you call it, you write down to enter your setup page 192.168.0.1 and sometimes be 1.1 depending on your router and the configuration. So that's your IP address. For those who do not know what an IP address is, that's how an IP address looks like. I think by now you know there is a local IP address and there's something called a global, a public IP address that's being stored. So each one of them will have a unique public IP address for other people to contact you. Although in your subnet, you'll have a unique IP address to use that's different from the global one. Don't worry, this will be clarified in the next few slides, but I just want to remind you how does an IP address looks like. And then you have a version 6 one, which is not being employed heavily. And why do we have a version 6? Does anyone know? Yeah?
Because of the normal 5 addresses?
Exactly, so that's we are done today. So mainly is knowing that there are no spaces. There are like 4 billion IP address version 4s, but they were not enough. They were run out. Because what happened in the beginning, what do you think happened?
It's irrelevant to that, but does it really go, why does it go higher to 225?
What is it?
Why do you go to 225? They are, and the ranking of the actual start,
2.5.
is it 255? Yes, I'm so sorry. You're exactly right. It goes to 255, isn't it?
Yeah.
So 1 plus 2 plus 4 plus 8 plus 16, 32 plus 128 should be a, yeah, 255, is it? Yeah, the masking of 255. Great. Yes, it goes to 255. But we don't use 255 usually. Usually we leave it to as the masking of the actual address. Why the 4 billion is run out? What do you think? What happened?
7 billion people now.
Okay, but not all the 7 billion have an internet and using the actual PCs. How many do you think? What happened? What really happened? Because not just an IP addressing, we have some sort of a masking addressing that divide those numbers into different numbers. We have this CIDR, which we're going to explain on one stage, dividing your actual networking part into different numbers. Why do you think these run out? What happened in the beginning? It's a matter of just corporation trying to be what? Trying to be greedy. In the beginning, they tried to end up with sending IP addresses. So they tried to buy like 10, 0, 0, 1, 2 as 10, 20, 0, 0, for example. So they stored, located all those addresses between, and they said we are going to use it within our company. Like IBM stores all those addresses, and we're only giving it to people within IBM. There are actual IP addresses not being used at the moment, but they think they will be using it at one stage in the future. So in a matter of fact, people just bought extra IP addresses just to keep it safe. It's just like saving everything for the future. Therefore, we needed another type of IP addressing to cope on with a large number of users. There's no 4 billion users at the moment, but there are a lot of people who actually bought extra IP addresses to keep it aside. IBM, 3Com, Apple, put anyone you want, Macintosh, that's the name of it, who bought IP addresses aside. So, returning to our analogy of forwarding and routing. What's the difference between those? That's the packet who passes on to as your destination. What's the difference between forwarding and routing? This is two terminologies which used by so many people as they are the same. Forwarding, routing, they are the same in my head. I'm just trying to pass a packet from one destination to the other. But they are two different things. Forwarding is just a matter of one router, where you try to move a packet from a router's input towards an appropriate router output. So in other words, that's your router. Imagine you have one connection as an incoming link and another connection as an outgoing link. The forwarding process is passing on that packet to us here. That's forwarding. So the involvement on one router, that's it. That's forwarding a packet. And we had the forwarding process within your MAC addressing, where you had a forwarding within your switch. There wasn't routing, there was forwarding. Two different things. So what is routing then? Routing is determining the route taken by the packet from the source to as a destination. So in analogy part is a process of getting through a full planning check from the source to as a destination. So if I would have that topology, the question is how I'm going to send this packet towards which route, which direction exactly, why. So that's where you need your routing algorithms to decide. I'm going to decide to go this way, passing it on towards my destination. So if A sending to B, routing means you're trying to pass on the packets through all your interchanging parts towards your destination. So in other words, however routers you have, you need to try to put the route in advance to reach your destination. The question is how many different types of routing algorithms and techniques are available. We'll discuss that later. But the main thing you need to understand, forwarding is move a packet from a router's input to an appropriate router's output. One router only. Meanwhile, routing means determining the routes that are taken by packets from source to destination. Not just that, when I say packets, how many packets belongs to one message? So you might have a message that has, for example, 4 parts of packets. So you have 4 pods trying to get from source A towards the destination B. It's not necessary that a route will take only that path towards a destination. Those packets can go any route. The main thing, they arrive to the destination and therefore they will be reconsidered as one packet or one message in the end. Okay? So routing is different than forwarding. And we discussed that in details in a minute. Who decides the route? You remember, let's go back towards your plug and play analogy. So if I said we have a switch that provides plug and play, it's usually where you have an actual device configuring itself, creating its own table to pass on the message. When you said you write down your entry, therefore creating your forwarding table of your actual switch tables. What about your routing? Who decides? So I said, what do you think? So this is your, let's make it clear. This is your forwarding table of a routing algorithm. So here I'm using the words routing and forwarding together, okay? Here as this one is a local forwarding table where you have a header value with an output lane. Just to clarify, in the last lecture where we described how we are creating a switch table, in the address, what we did, we had 2 things. We had an address with what? Source and destination. And what were these? They were MAC addresses, mainly. In your IP addressing, it's exactly the same, but you have an IP address instead. And in the header file that you receive to do the forwarding, we will depend on a short numbers of the IP address, i.e. taking a prefix of the actual full IP address to know your actual forwarding destination and which interface to go on. So same analogy, same thing. You receive a header packet. You have a direction of numbers. So let's say you'll have 0111, and that's in your table referring to interface number 1. My question is, who decides that table? Who creates it? Is it an auto configuration? Or is it an admin? Or is it a routing algorithm? Was it? The routing algorithm itself. the routing algorithm decides exactly how to pass on and which route the packet should take. Because there are 2 different, or 3, 4, 5 different algorithms. I'll give you 2 examples. Let's see, if you have a wireless connection, okay? Do you know number of users inside that wireless connection? So let's say you have a university campus. How many users do you have using the wireless connection? You never know. You don't have numbers or names. So let's say you have 5 users. If I want to have that connection between those 5 users, A, B, C, D, E. If I'm trying to use a wireless connection between those 5 nodes, how would you create a table? Again, depending on your routing algorithm. Simple as that. So there are 2 types. One will say that if I need to send an information, I'll just send a request, creating a path between. So I will send a message to E, asking E, do you know where B is? And usually B will send a broadcast message or a request message to other users. So therefore, you create a link based on your information, like a proactive link. It's not being connected. You just assume there is a user called B and try to send an information to that. Don't worry about how you create a table. It's not going to be part of your materials. But I just want you to understand, the routing algorithms decides how the table entry are. It creates your forwarding table inside that node, depending on this criteria. So if I would say, okay, after creating that link between all the nodes, which path do I take? If your criteria is speed, therefore you need to have a connection to the lowest cost path from the source to destination. When I say cost, sometimes you have a number here associated to a link referring to the condition or the actual bandwidth that you will consume. So if I say I'm trying to get to C through So if I would say I want to get to from A as a source to where C as a destination, okay? You can choose any path you want. But I want to ask if you try to deliver it towards the destination C with the lowest cost, with the less cost or the shortest path. Which one do you go? If I say shortest path. B, C. Why do you choose that path? Is it shortest? That's 1, 2, 3. Meanwhile, this are 1 and 2. So shortest path at the moment is going through E and C. That's it. Meanwhile, if I ask you what is the less cost or the less condition link between your source and destination, the numbers are referring to your conditions. Where do you go? Your path should be this time A going through E, B, and C. Because the number here is indicating which will be most more effective or efficient to go through this path instead of going to the shortest one. Again, depending on your requirements, the routing algorithm will decide eventually where to go and how to go to that link. Today we're taking what we said, the link state shortest path, and I'm asking you to do it today practically, and I'll do it again. I have 2 examples. One of you ask me to do it, and then you do the other one. But I need you to concentrate in the next 3 slides I'm going to give you. Before I move on, any questions? Is it clear what forwarding is and what routing is? That's what I want you to understand the most. Okay. Can you see the letters inside those routers? In the back, can you see the letters inside of those circles? No, right now. Is that fine? No? Can you see the letters?
There's a ball.
Make them white. Can you use the link? I think that color is better, is it? I'll just stick with this color, okay. So first of all, check your notes. You see them in the notes at the end. Let's see how this topology is created and what I'm interested in this topology. First of all, I have a graph abstraction. First of all, the graph is defined by number of nodes and the edges connected each node. So, for example, I'll have nodes at the moment are between U to Z. That's your routers. That's your nodes. Okay? I'm calling the nodes at the moment as a router. The link. What's the link between U and V? What's the cost of the link between U and V? Just 2. That's your actual edge, which is the cost of connection between U and V. Simple as that. So if I would say the graph consists of number of nodes and consists of number of those edges between those nodes. Simple as that. Your number of nodes or set of routers at the moment goes from U to Z. Meanwhile, your edges, those set of links, they are consistent of 2 links. Therefore, if I have a link between, at the moment, this example, A and E, the edge between them will cost, so therefore your connection will be A, E. Simple as that. So it's a direct adjacent connection. It should be a direct connection. So if I say, what's the connection between A and B? There's no direct connection. You cannot create a link unless I put that line, therefore you have that link. So it's a physical connection, an adjacent connection between 2 direct nodes. If you don't have that direct connection, don't create that link. So E and B, simple, there is an E and B connection. The cost of that connection will be 1. Is that clear? Any questions? Good. Look at the slide this time. So here I'm defining the cost. So the cost between a node will be actual value on that link. So the cost between W and Z is the actual connection on that link. And the cost is being written as a number between them. These numbers, I'll give you the numbers. I'll just give you the graph and ask you to construct a table called the Dijkstra algorithm table eventually. How much is the value between, for example, if I say try to connect between U and W with the shortest path. Let's choose between U and X. Not the shortest one, but the least cost one. What is it? So either it's 4 or either it's directly 1, is it? How did you manage to make it 4? What was the formula to actually find the number? What did you do? Give me the formula. So if I say I'm trying to connect U to W, what do you do? What's the formula to give me the costs?
You set all the connections out together.
Exactly. So it's double connection. You be careful. So what I'm doing is the connection between U and V, for example, plus the connection the connection between U and V plus the connection between, for example, V and W. What's the connection here? What's the values? So that's 2 plus 3, for example.
5.
We'll give you 5. Simple as that. Yes.
I'm a short one. You go to U to X.
It depends. If I'm asking you for shortest regardless of the link state, i.e. go for the shortest. But I'm more focusing on the actual cost, i.e. the numbers. So I needed to have the lowest cost number in the end.
Is there much difference between that and how many?
It depends on the routing algorithm. But with the link state, this link state, which is Dijkstra, I'm going to show you in the next 2 slides, it depends heavily on how to route towards the least cost connection. By the way, what are these numbers referring to? What do you think? Sorry? No? No time.
Just
Might be a distance. So in other words, the bigger the number, the longer it takes to arrive towards the destination. So it might be condition, it might be distance, it might be anything else. It might be number of users on the link. It might be a fault, an actual delay. So therefore, the highest the number, the more time will require to a packet to arrive towards the destination. Therefore, you need the least cost path. Simple as that. At the moment, is this clear? It should be basic and simple. Any questions? Perfect. So, this routing algorithm will say define the least cost path eventually. I'll show you how to do it in whatever we get there. Let's see what are the routing algorithm classifications. There are two types of classification. One classification is static versus dynamic. Let's go there first. What do you think the difference is between static and dynamic? It says static routes changes slowly over time. Meanwhile, dynamic changes more quickly. Can anyone explain this? how do they change? They physically change? Do they number change? What happens? So if I, yes,
I'm going to guess that dynamic, because once it establishes a link, it knows the route and will be able to do it quicker. Whereas static, I'm going to say because it knows where to go, it can carry more stuff into stuff.
no. It might be having advantages for one of them on the other, and then we explain the advantages and disadvantages, but that's not the reason of static and dynamic. What do you think changes in static and dynamic? What is that?
No, I would imagine the dynamic nodes could disappear quite often.
Okay. So the reason for having this dynamicity is whenever nodes goes out from the connection, therefore you need to have some sort of a refreshment, because if this is a wired connection, let's put it that way. If you have a wired connection between 3 or 4 nodes, there is very little chance of those nodes moving anywhere else. They are stuck on the table. Go to the library. You'll have those machines every day, everywhere. You just go and put in your username and password and start using it. They're not changing. But again, that's not the reason. That's not only the reason. I'm saying, not physically, I'm saying the root. What else do you think? That's fine. That's that. Sorry?
You could find a faster route.
Can't find a faster route, therefore these number changes. So in other words, if you have this number at the moment in the previous slide, number 5 might goes to this 5 connection between U and W, the long one, might be 2 at one stage because there is no long users on it. There's no more users using it. Therefore the numbers might change that one. This never happens very frequently, but it happens, depending on how your physical topology is. So again, static, our routes change slowly over time, meanwhile with dynamic, they change quickly. Depending again what kind of connection, whether I'm using a wired or wireless, therefore when you mentioned that example of nodes going out of the connection, therefore you need to have that dynamicity rather than a static. Because if you try to connect B, who's not at the moment of the network, you never get to B. So you need that dynamic update of your table, the dynamic update of the connections, depending on the connection. Maybe that's a wireless connection. With wired, would be more fixed towards static one. And again, the direction and the route of those arriving towards the destination might change depending on how heavy you use those routes. What about the other classification? Global and decentralized. So global is a centralized, where you have all routers have complete topology link cost information. So what does that mean? For example, the graph I showed you before, I have the number already been stored inside those connection links. And each one of those routers or nodes know exactly the cost to connect that node. So in other words, you have the full information of the topology of the network. So you know where to go if you ask you to go for the least cost path. So this is being defined to all users before they start. And this is what we something use as called a link state broadcast, where you send information asking for the link connection. A decentralized one is a router's nodes physically that connected to the neighbors. So each node will have a direct connection to the neighbors, and you only have that link value. So therefore, let's say this is A connected to B, and this one is connected to C, and C is connected to D. A only knows the connection between B here and C. Meanwhile, he doesn't know what happened between C and D. That's a decentralized one. You need to ask C to tell him exactly what's the connection. In some cases, this is useful because you don't want to have all the information, therefore creating issues with the overhead. And sometimes those updates happens between those nodes, you don't know about them. So sometimes it's better and useful. Those are the decentralized ones. How they clear those clarification? Any questions between the dynamic, static, or decentralized and centralized one, or global? Yes? The global is a centralized one, where you have all the information. That's what we said in the previous slide. The graphs show the full connection. So if there's a number here, you'll say there's a 3. A would know the link between A and B is 3, between A and C is 1, and between C and D is 3. A will have all the information. If it's not a global, a decentralized, he will never know what is here or here. He only knows the adjacent connection, the direct connection between his node and the neighbors. So if there is a direct connection here, he will know the cost in here because it's direct. Is that clear? Questions? Good. So I'm going to go now to, I'll give examples here. The global one is the link state I'm going to use as a routing algorithm. Meanwhile, the decentralized one is called distance vector. I'm not going to cover this here. Okay? So we focus on the link state, or known as decentralized algorithm. Okay, let's focus here, because I'm going to do this practical example afterwards. A decentralized algorithm is a network topology that link costs known to all nodes. Why? Because it's a global or a centralized connection, a classification. One, it's accomplished via what we call a link state broadcast. So each node will broadcast the link connection between the node and direct to the other nodes connected to it. From the beginning, so you create the tables before you start sending any information. It's like a self-configuration part. You tell everything that understood, then you start sending information. All nodes will have the same information. So the update will happen once. Not in each node will have a different update. So therefore you'll have a node having different information or values between links. Meanwhile, a node did not receive that update, therefore it will be an issue. All nodes will have the same information at the same time. It computes the least cost path. So I'm looking here, what's my criteria? It's the least cost path. That's the main thing. From one node, i.e. the source, towards all other nodes. Not just the destination, all other nodes. It gives a forwarding table for that node, and eventually you have iterative after a k iteration, known the least cost path to k destination, and that will be the reason of that order. It's how to know the least cost path towards all the nodes. I want you to understand this notation. One, the connection between two direct nodes connected, for example, x and y, is the link cost from node x to node y. So what does that mean? That means, let's try to be clear here. So please ask me a question if you don't understand, because that's the part where I try to clarify everything. Let's create a very simple topology here, okay? I have A connected to B, B connected to C, and this node is connected to D, and that's back to B. And let's put values here, 2, 3, 1. Okay? So let's try to explain first thing. The connection between X and Y. So in this case, let's say I'm trying to find the connection between A and B. What's the value? 1. Simple, straight. I'm just finding the edge. If I would say, what's the connection between A and C? Although I just have A. Be careful. The question says, link cost from node X to Y. If it's not directly connected, there's no direct connection. We put finite value. So, is there a direct connection between A and C at the moment? So the value should be finite.
Could you explain again why you don't go through the others?
At the moment, you just have A in your table. So you don't have other nodes to route through. It's like, this is not like an intermediate node. If I don't ask you, or don't give you B as an intermediate node, you cannot use it. So you are only able to use the direct connections. If I would say, yes, you have B in your table, therefore you do that connection, which I'll explain in the next.
So it's not decentralized.
Yeah.
Don't worry about this global or not. That's a classification I don't want. No, this is a global. You have all the information, but there's no direct connection. That's what I'm worried about. No, this is link state. You have all the information. That's the global one. Because you will know all the values. That's not the worrying part. The only part you don't have is you cannot connect through B. What I want you just to understand at the moment is if there is a direct connection, put the value. If there is no direct connection, put finite value. At the moment, is that clear? First step. Good. Let's go to the second part of the notation. A D to the V means the current value of a cost of a path from source to destination B. I'll create a table, and therefore I'll put something called DV in it. DV means your actual value between A and B. In this case, it will be 1.
How do you know it's between A and B?
I will say this will be A connected through B here. I'll show you in the table full details, don't worry. I want you to understand the notation. Hopefully that will not mix things because the table should be easier to understand. Because the table will look like this. This, no? Yeah. Okay. Yeah. So let's explain the notation. S step are the number of steps you're going through. N is the number of iterations, the number of nodes that are going to be inside your table. So you ask me how do you know A and B? At the moment it's you trying to get connection towards V, W, X, Y, and Z. That would be destinations inside those packets. Let's go back to the notation. So C towards your connection, that's your connection value. You should have a direct connection. If you don't have a direct connection, you put the finite number inside. Infinity. Okay? There's no direct connection. Infinity. Okay? D to the V means the current value of cost of a path from the source was a destination. A P to the D, that means a predecessor node along a path from source to V. So, if I would say the DV, let's put it this way. That's your D to the B, and then DP to the B as well. That means the value between the source and B, and what kind of node you're using to connect B. So in this case, will be 1. I'm using A as my connection. That's it. If I say, for example, the same thing, A and D. So I would say the value of D with the predecessor node of D. So I'm using A as a source. So what's the value, first of all, between A and D? 2. What node I'm using to connect? I'm using the source itself, A. Simple as that. Should be clear whenever I go to the exact example, I'll show you full details.
Why
And
should
fine.
this?
Sorry.
Why isn't that, the A? Why couldn't it be the B?
It can be if it's in the table.
In the table.
I'll say you start from source to as a destinations. So I'll give you the source. So the source should always be in the table, and you start from that source. I will be clear hopefully in the next example. And it's the set of nodes whose least cost path definitely are known. So whenever you find the shortest path, then you put it inside the table to use that node to route through. I know, is that clear? Show you the next step. I'll leave this one, this will complicate stuff. I'll go back to it after I explain the full details. So let's go to that. Go to your notes to that slide so you can make sense what I'm doing here. I'll say in the example, I'll say I'm trying to find the link state or these are link state or link cost path, the lowest or the least cost path between the source U to all other nodes. So I'm identifying U as your source. Okay? So you start from U.
Is that what N stands for, source?
Sorry?
Does the N stand for?
N are the number of steps, number of nodes. N is a set of nodes whose least cost path defined is node. So eventually you'll have all the nodes inside here. You have to answer it, don't worry about it. I just want to do it in front of you where I ask you to do the other one yourself. So I want your help with this one, okay? Let's do it together. Let's do it on the board. Let's do it on the board easy. So you need to create that table. And you need to use your link topology, the actual topology of the connection of the graph to find out the details. Okay? So first of all, you have the number of steps. You have the number of n, the actual iteration of the nodes. The least cost path will be written in here eventually. You start first of all with, you can't start in any order. There is no right order of doing it. I'm giving you U as your starting point because U is your source. Put them in any order you want. So I'm putting them in the alphabetical order, if it is P, W, X, Y, Z, yeah?
Where did it say what the source is about?
It's not written here, but I'm giving you the actual order. You should say in the example, it starts from a node. It might be X, might be W, from anywhere. In this case, it's U as a source. You start from U. Okay. Let's do it together. I'm I'm trying to look at the notes or in the actual board, the links. So I'm trying to find from the source, U, towards those destinations. So first of all, is there a direct connection between U and V?
Yes.
What's the cost and what's the node I'm using?
The cost is 7.
Cost is 7. I'm using what?
U.
Exactly. That's how simple it is. Can you continue? I'm trying to connect to W through U. What is the cost between U and W? Direct connection. 3. Using U. So, now I'm trying to connect to X. Give me the value.
5.
5. We're using. Give me now what I'm trying to connect between U and Y. There is no direct connection. Is that right? There is no direct adjacent correction. I need to use either X, W, or V, which I cannot at the moment. What about Z? Same. No direct connection. Is that clear at the moment, everyone? Should be clear. If you don't understand it, let me just explain it again. That's the first step. That's fine. Just. Is that okay? Sounds okay.
So,
okay.
sorry.
Yes.
The D is the destination, the P is the value, or is the
The
P?
D is the value.
The D is the value,
The
the
P
P
is
is
the
the
actual
destination.
predecessor
The
node,
source.
not destination.
The source.
Predecessor node. What I'm using to connect, because destination at the moment is V.
Oh,
Meanwhile, I'm using U as my connection, not
the
destination.
node.
Yes. What are you using? Which will be clear in the next step. So, what do you do? Okay.
Is anything to go?
Yes, for U, Y, and Z. Go on that back. Is there?
For T and P.
Oh yes, you don't mention because there's no connection. What do you put there? There's no actual node being connected. So there's no connection. Use it as no connection. That's a no connection. Okay? Step number 2. What do you do next? So next, after this, you need to choose the shortest, or the less, not the shortest, the least cost path. And what is the number that at the moment indicates the least cost path? So you just choose 3. 3 are belonging to W. So therefore, step number 2, therefore you have 2 nodes at the moment. U and W. So you're creating now your path. You're creating your route. So now you have 2 nodes to use. You do the same operation, the same iteration, but using 2 nodes instead of 1. If you get a least cost, a lower number, you put it there. If not, you stick with the old number. Let's do it again. I'm trying to connect V. Now I have U and W. Will I have a lower connection to V?
Yes.
So if I go now, what's the value?
6.
What's the formula? So the formula is the connection between, at the moment, is U and V plus the connection between V and W. Is that right? V and, what is it?
Yeah.
W and V. So that's 3 plus 3, 56.
6.
Is that right? Is it clear, everyone? What's happening? Is it clear? Any questions? So, look back to the graph. So I'm trying to find the least cost path between U at the moment and the first, now we have V. If I use the old path, that's 7. But now I have W to use. So I can use any connection through W. So that's 3 plus 3. I'm just counting the connection values. 3 plus 3, that'll give you 6. So 6. What node I'm using as a predecessor? What is it?
W.
Exactly, just using now W instead of U. So in reality, you are sitting here to connect to the V using W. In the previous iteration, there was U only connecting, so you're only using U. In this iteration, you start using W as well. So you write W as your predecessor. W, you just skip it now because we already find out that W is part of our connection. We are using W, so you don't need to do it again. Now X, what's the value connection? Using W or not, and what the predecessor node is. U trying to connect to X. Same value or different? Why is it not different? Why is it not different? Why is it not 3, 4, why is it not 7?
The
It
shortest
costs
link.
more to connect through W. So I'll stick with my old connection. Is that clear? So I would not change my connection even if I had a different node, I'll just have more cost. I needed to have the least cost path. That's the criteria. Least cost path. What about Y? Do I have a connection to Y this time? Or is it?
Yes.
What's the value? It's 11. What's the predecessor node? Is it clear what's happening, guys? Yes? U plus W. U to W. What's the connection? Plus W to Y. What's the connection?
Oh, yeah, I was in the
Oh no, the letter. Be clear with the letter. That's the Y. So that's 3 plus 8.
yeah.
So what I'm doing here, exactly what I'm doing is connection between U and W plus the connection between W and Y. What's the value? That's 3 plus 8. That will give you 11. Yes?
Then W from U, and then through V, and then.
Can you go to V? You cannot go to V because you don't have them inside your iterations. You cannot use any node. You just use the nodes that you have within your number of steps. Is that clear? Let's continue. What's the value between U using W to Z? Is there a direct connection between those two nodes?
No, incorrect.
What do you bring down? Which one? 5, which is? So that now you'll have second step, number 3, number 2, that will be U, W plus. So now you can link between U, W, and X. If you get a least cost path with those 3 nodes, by all means you use it. If not, you continue with the whole number. Yes?
Because it's a U, doesn't that make a difference?
What do you mean it's U?
Don't have to do it.
No? Why W? Which is the least cost path?
Yeah,
What is it? 5, which is X. So it's U, W, and X. You add it to the link, so that's the path now you have is U, W, and X. And you continue with your path. So, what's the connection? So now we've taken down, you can put them this way to just indicate to yourself. Continue the table. What's the direct connection between U and V? Is there a lowest path using now X or W?
Same one before.
Same. It will be more if I go through X to W. That's 5 plus 4 plus 3. So that's not worth it. So just stick with the whole connection. And that says what? 6 using what? Why is it? Oh, you asked me what this did you? Did they change this? Oh yes, yeah, that was W. Yes.
Yeah, that was.
So this is W as well. I'm mixing things. Okay, I'm trying to connect now. I skip as well. W is already in the table. I skip X already in the table. What about Y? I'm trying to connect Y through W or X. Will I have a lower connection? What do you think? Is it the same?
Yeah, one.
So the same 11 W. Yes?
What would happen if there was a shorter route that would take you back, say like between...
Oh, okay, wait 1 minute. Shorter means something, least cost means something else. I don't care about shorter. I mean, I need to stick with the numbers. Least cost path.
What if there was a least costing path between U and X that would cause the next step for it to go back?
You go through it if it's part of your path. If it's not, if that node is not defined, you cannot go through it. So I'll give you an example. You just in a minute said you trying to connect. Which the example was? If I would say the least cost path between U and V is 7. If I don't have V, if I don't have W to reach V, is that right?
No, I mean, because we've gone to U to W to X,
Yeah.
and then from X we'll look for the next shortest path,
Yeah.
which would then be U. So that means you go backwards.
You don't go. You just
I
stick
stay.
with the old one. It's not like you go and then you return. You just go to the least
No,
cost.
it would just stay.
No, it's, you choose either one. Yeah. Z, is there a connection?
Yes.
What's the value?
14.
It's not 9, it's 5 plus 9.
Yeah, 14.
It's 14. What's the predecessor node?
X.
X. Let's continue. What do you bring down now? What do you add?
V.
You add V. So that's the least cost now. So number 3. Now U, W, X, and now you have V.
You sure it's 14, isn't it?
5 plus 9. Trying to connect Z through X. Alright? So now you brought this down. You have now left just 2 nodes to check. The first one is Y. Is there a lower connection using your W, X, U, and Y? No, U and V.
How's it connected to V?
You tell me, how's it connected to V?
Through W.
What's the least cost? What? Tell me the path. U, W, V. That's 6 plus
10.
it's 10. 3 plus 3.
That's a short, isn't it?
Yeah, that's a
You're
solid.
trying to get to 1. So it's 3 plus 3 plus 4. How much did that give me?
10.
What's the predecessor node? What is it? You just started mixing things up now. There's nothing with it.
What?
Okay, guys, let's I need concentration, guys. Is this clear? Everyone, is this clear? What's not clear, just tell me so I can explain it. Let's start here first one.
So do you know like
Which one?
for the first one?
Can you keep it quiet, please, guys? Keep it quiet, just to concentrate, guys.
If I can show you.
Okay.
Like, here you started from W.
I haven't started from W. I've just moved on from U to W, then W to the destination. You're starting from the beginning. You start from the source, but you use other nodes as an intermediate nodes to connect to the destination.
So we always
You always start from W, from U, the source. You always start from U. You don't start from anywhere else, and you start counting. You do the full connection between. For in this case, U and W, and connection between W and Y. That's what you're using. You start from the source, and it's the source only. Someone will be sleeping, that's fair enough.
Yeah, but that's 11. How come it's 10?
How is it 11? Just let's do the math. 3 plus 3, how is it? Plus 4. Is that 11? For the love of God.
It did this.
That's
Okay,
10.
sorry. I was thinking about it.
Sorry? If they are, that's a good question. If both of them are the same, choose either one of them. Because in other cases, then therefore you will have the other one in the next step. So it will eventually be the one of the least cost path. Let's continue finishing it and see what we'll end up with. Tell me the connection between Z. Now, between your source and Z. What's the value and what? Try to find the lowest path using, don't be every node, using the nodes you have, which are U, W, X, and V. Let's try it.
14.
Is that the path then? So it's gone to...
Yeah, let me ask the question first, and I'll go back to you, okay? What's the cost?
I think it's 14.
It's still 14. There's no lower path, is it? So you just stay with it as a 14 using X. Sorry, change your question.
So you go U to W again, and U to W to X, because they all link.
Yeah.
Then U to W to X, into V.
It's not, no, you don't always go to it. Unless you need it, you go through that path. If you don't, you stick with your lowest number. I'll leave it to later on. Okay, guys, let's continue. What do we bring down now? Which one is the lower? So now you have the path as U, W, X, V, and Y. Through Y, do you have a lower connection to Z? The only node left is Z.
12
What's the predecessor node?
is U, W, W, V, V, Y,
U, W, V, Y,
Y,
and Z.
Z. Yeah.
That'll give you. What's the predecessor node?
What?
Using what? Y?
Y, yeah.
What's now you bring down? The only node left is Z. That's your path now. The path is U, W, X, V, Y, Z. Phew. Sorry? That's a good question. I don't know. Haven't decided yet.
Only 5 months.
So, is this clear? Fair enough, it's the first time, but the concept, is it clear?
Yeah.
Yes, please.
How do you know that you have to go from U rather than in the beginning?
You start with U by default because it's the source.
Is it,
You must
is it
start
defined?
with U. Because I'm telling you, the source is you. So
Okay.
you must start from you.
Oh, I see.
This is you trying to connect other people.
That makes sense.
Okay, let's see the slides afterwards. I'll give you a chance to practice, don't worry, after the break. But just have a look. That's your full answer of the most.
Four is 1.
Okay, let's explain this one part for the last time. Come on, guys. Just keep it quiet, Elizabeth. Come on. The first connection, I'm trying to connect U to all other nodes. So the first thing, you see the link, see the actual graph. I'm trying to connect U to V. The only direct connection between U and V is 7. Using the predecessor node, in this case, is U. So that's 7U. The second destination is W. So I'm trying to connect between U and W. The only direct connection, which is the least at the moment, is 3, because there's a direct connection between U and W. And that's 3 using the predecessor node as U. If I have a destination as X, then therefore my direct connection, the only connection, is between U and X, which give a cost of 5. And that's a 5 predecessor node as U. Meanwhile, the second destination is Y. Do I have a direct connection at the moment? I just have U in my table. I cannot use X, W, or V. Therefore, there is no direct connection. Z will be the same thing. There is no direct connection. After the first step finishes, we need to decide which node to bring down. And in this case, it was W because it has the least cost path. So now in my table, I'll have U and W. So instead of having now U to connect every destination you have, you'll have U and W as well. So let's look at the second destination. So I'm trying to connect between U and V. Now I have W. So instead of going the longer route of 7, I now can connect through W. So the cost between U and W plus the cost between W and V. And that is 6. What node am I using as a predecessor? If I reach V, that will be W. So I'm starting here. What's the node I've connected predecessor was W. So that's why you have W inside your table rather than U. Because I've used W to connect to the destination. If you look at the X, it will be the same. There's no changes because if I connect through W, that will give me a longer, a most cost path, a higher. 3 plus 4, that gives me a 7. So I don't write 7 here, I stick with 5 here because it's least cost path. Meanwhile, now I look at Y. Do I have a connection this time? I'm using W, so therefore, yes, I have, because U to the W, there's a cost between U and W 3, plus the cost between U and Y, the long path of 8. That's 11, therefore. That's 3 plus 8. What I'm using as a predecessor node? W. Until now, I don't have a direct connection to Z. There will be no connection. What do I bring down now? It's X. It's the least cost path. So I bring X down. Now I have U, W, and X to connect to my destination. What do I do next? I try to make now sense of all the directions. So therefore, I'm trying to look at V. Using U, W, or X, can I have a lower path? A least path. A least cost path. No, it will be still 6W. looking at, I skip W and X, they're already in the table, I don't need to do it again. Now I have Y. Again, Y will be the same, no changes, it will be 11W. Meanwhile, now Z, if I'm using U, W, and X, I can go to Z. Either the root of 3 plus 4 plus 9, or 5 plus 9, which will give you a lower path, therefore a least path, it will give you 14 using predecessor node as X. Until now, any questions? Is this clear? Okay, fair enough. What do I bring down? I'll bring down the V because it's the least cost path. My node now would be the path between U, W, X, and V. Now you only have two nodes left, that's Y and Z. Do I have a lower connection now, least connection between U, W, X, V to Y? Yes, you will have that. If I go through 3U, 2W, that's a 3, plus 3 between U and V, that's 6. V to Y plus 4, that will give me 10. Therefore, I have a least cost path now, that will be 10 using V as a predecessor node. With Z, it will be the same, no changes. What do I bring down? I'll bring down Y because it is the least cost path. Your path now at the moment will be U, X, U, W, X, V, Y, and the final connection will be to Z. There is a lower connection going through U to W, W to V, V to Y, plus Y to Z. That will give you 12, using a predecessor node as Y. That's it. That's where you constructed the shortest path tree by tracing a predecessor node. Okay, I'll give you a break for 10 minutes, and then we'll do another example, okay?
Yeah, question?